Good morning, everybody. It's just about 11 o'clock. We're about to start our webinar on using ANSYS solutions to help improve electronics reliability. We're going to wait just a couple minutes to allow a few people to download the most recent plugin for GoToMeeting before we get started. Okay, Metin, you want to go for it?
Good morning, everyone. Welcome to our webinar on solutions to help improve electronics reliability. We have two great presenters for you today, and it's we are not going to take up the whole hour. We are going to present this in a short format so that you have plenty of time to ask questions, as well as have extra time to be able to view the contents of this webinar. So with that, I'm going to turn it over to Glenn, our first speaker. Glenn, please go ahead.
Okay, thank you, Metin. Welcome everyone to the first of 5 short webinars Ozone Engineering is offering on electronics reliability. My name is Glenn Compton. I am joined later in this presentation by one of our senior electrical engineer consultants, Daniel Ismaili. So electronic systems are found in nearly all industries, everything from aerospace and automotive to consumer electronics and healthcare. As such, ensuring these systems remain operational and perform their intended function in a variety of environments is critical to product success and customer satisfaction. Companies who properly address electronics reliability concerns through simulation can meet many of the objectives stated here. Traditionally, companies have used a design, build, test, and then break and fix it design cycle. As I'm sure you know, this approach can be expensive and time-consuming. The design rules and best practices associated with this process may not provide engineers with enough guidance to properly design modern, cutting-edge products. By using simulation, virtual prototypes can be created and tested virtually. This provides engineers with a higher degree of confidence that the eventual physical tests they do run will be successful. Performance, safety, and cost are all critical considerations in the design of electronic systems. Designs are required to reliably perform their intended function in a wide variety of demanding environments. If electronic systems get too hot or have a mechanical failure, they may not be able to perform their intended function. In some instances, think automotive, aerospace, and healthcare, this could put people at risk. A wide range of customers have benefited from ANSYS electronics reliability solutions. Benefits typically include reduced design development and material costs, reduced product development timelines, and improved product performance and reliability. Engineers must address a wide variety of design requirements when designing electronic systems. These range from electrical, such as signal and power integrity, thermal, such as the implementation of optimal cooling strategies, or mechanical considerations, including the ability to withstand thermal cycling, shock, vibration, and drop. Additionally, products are expected to meet life requirements to ensure they meet their intended function for at least a specified amount of time. Engineers also need to consider the effects of manufacturing, transportation, and product operation as a part of their design process. ANSYS provides a suite of tools and workflow solutions that address a wide range of electronics reliability concerns. Each simulation toolset plays a key role in the understanding of how electronic systems operate and perform in a variety of applications. Over the next 4 weeks, we'll feature each of these areas of focus in a separate short webinar, but I will summarize the challenges of each now. Printed circuit boards, ICs, and IC packages are used in almost all electronic products across all industries: automotive, A&D, consumer electronics, healthcare, and energy. With electronics getting smaller, engineers need to design boards that are smaller than ever and incorporate all the required features. Accurate modeling and simulation of these components are key to reliable end products. Electrical simulations help address concerns related to signal and power integrity, EMI, EMC, and others. Maintaining thermal integrity is an essential part of designing best-in-class electronic systems. Thermal simulations allow engineers to evaluate and optimize cooling strategies, for example, forced convection approaches using fans versus natural convection in component designs such as heat sinks. Using ANSYS tools, users can evaluate thermal performance from the chip die level all the way up to the system data center level. Users can also consider downstream effects such as thermal mechanical effects such as PCB and package warpage and stress. Being physical structures, PCBs and other electronic components are susceptible to failure due to excessive deformation and warpage, shock, vibration, drop, and other environmental conditions. Structural integrity needs to be maintained to help ensure electronic devices perform their intended function. ANSYS has a wide variety of solutions for quickly preparing high-fidelity simulation models that can be used to assess the mechanical performance of electronic systems. By their nature, electrical devices generate heat when in operation. It is important not only to characterize the electrical behavior in an electronic system, but also the thermal effects that arise from its operation and potential environment. In turn, the deformations in the structure itself, potentially serving as the cause of mechanical failure in PCBs, packages, solder connections, and other structural components. Therefore, when simulating electronic systems, it is important to consider the problem holistically by considering these various multiphysics effects. Having a good understanding of an electronic system's electrical, thermal, and mechanical performance under various conditions is important. Taking these models further, reliability physics analysis tells us how long a product is expected to last under such conditions. Tools like ANSYS Sherlock can be used to determine the time to failure or the cycles to failure for all the components on a PCB using various inbuilt reliability models. To explore the study of electrical reliability further, I'd like to introduce Daniel E. Smiley.
Hello, everyone. This is Daniel Smiley. Thanks, Glenn, for the introduction. Please give me a second to share my screen. Sure. Okay. Are you able to see my screen?
Yes. Thank you, Daniel.
You're welcome. So thanks, Glenn. As Glenn mentioned, I'm going to briefly overview of each capabilities and break out what are what ANSYS is able to bring in terms of simulation best practices. What makes ANSYS electrical reliability tools stand out is their ability to do an extensive range of simulation capabilities to capture all type of performance and showing their risk to designers and engineers. Simulation can start from a very small component such as transistor, go to a PCB level, and even go all the way to a system level. These software are able to simulate in a way that designer can carry them from one level to another. On top of that, you can couple these chip packages intersection to ensure full product functionality. Some of the examples are power integrity and signal integrity. As we all know, the switching frequencies has been increasing almost every year. That makes a lot of challenges for the new PCBs. It wasn't like that before, but nowadays, that high frequencies makes the coupling effect between different traces on PCBs. Hence, power integrity and signal integrity are becoming very, very important. SI-Wave includes the power integrity analysis in SI-Wave includes SI-Wave DC feature plus AC analysis to accurately model power delivery network and noise propagation on a PCB. Power integrity provided by ANSYS is ideal for analyzing power integrity distribution issues, automatically optimizing the coupler capacitor selection and placement for engineers and designers. Another capability in SI-Wave is signal integrity analysis. Signal integrity is becoming an increasingly important element of circuit and PCB designs. As frequency used within digital circuit rise, even short connections act as a transmission line, and they have an effect of their integrity of the signal being carried. This wasn't that much important before because the frequency of switching wasn't high, but nowadays it's very important. Hence, it is important to make sure the PCB passes the standards before even making the prototype, such as GEDC, because it saves a lot of cost and money for the companies. SI Wave can easily import different electrical CAD geometry, and it can provide significant insight into the channel performance for the designers. SI Wave also gives measurement of the amount of signal degradation when the signal travels from the driver to the receiver, which helps the designer to pre and post layout verification. And the designer can choose one driver and multiple receiver, or multiple driver, one receiver, or use all the traces in the PCB as a driver and also the according receiver to study that better. Another capability is CPA, or chip package analysis. As we know, SoC grows in density and complexity these days, so there is an increased need to account for the power distribution network. This applies to both chip and packages. CPA, or chip package analysis, uses 3D finite element method for package extraction, representing the parasitic in physical RLCK format. Red Hawk can provide bump resistance and inductance map to highlight and debug package weakness. So the designer know where the weakness is, they redesign it again before making the prototype, and again save a lot of time and money for companies. Another great capabilities is thermal simulation. DCIR is very important because, as we know, heat can degrade the reliability and performance of electronic devices. Power dissipation and power losses are the key input for these analyses. So the designer or the engineer can use SI Wave, and in the SI Wave software, they can run the DCIR. It gives them different profiles, as you can see in this presentation, the voltage, the current, and the power. So they can distinguish the hot spot. Once they do the analysis, the beauty is that they can also couple it with IcePack. So they export the data from SI Wave, they import in IcePack, and then they run thermal analysis. Another beauty is that it can be bidirectional coupling between IcePack and SI Wave. So once the analysis is done in IcePack, the output can be imported to SI Wave, and then it can update the material properties. So it can update the current density, for instance, the copper in your PCB board. This helps designer to accurately predict the operation temperature of electronic devices in different environments, so they don't face surprises when it comes to manufacturing. EMI simulation. As we know, I think it's very fair to say that EMI is the most critical aspect of any kind of electrical reliabilities, especially these days with higher frequencies. Designers need to make sure component devices, PCB and system works in broad range of electromagnetic situations. We can make the PCB and test them in the chambers, but that would cost a lot of money. Hence, this simulation will become very useful to save time and money. EMI scanner can help the designer because they can design the rules and give different thresholds for violation and warning, and then the checker automatically analyze and flag areas on the board with colors. It can also give you a table where you can see what net is violated, what net has warning, and then change the design accordingly. As we know, EMI can undermine the performance of high-speed electronic devices, so engineers can benefit a lot from EMI scanner. Transient or odd diagram, as you can see in this presentation, can also release issues such as overshoot and undershoot. These capabilities minimize verification for EMI compliance. Another important thing nowadays is antenna performance. As we know, consumer electronic has been growing each year. Tablets and smartphones are spread out more than ever. these days. And as you can see, we have a smartphone on the left-hand side of this presentation. So it is the overall system. Inside of it, it's a PCB, and inside that PCB, it's an antenna. So when the antenna designer is designing this smartphone, they need to think about the overall system, the PCB, and the antenna itself. So shielding, which ends up in location of the antenna, is very important. HFSS is one of the best tools to, it's actually the best tools to give this capability for designer, so they can design the antenna appropriately as well as its location. So we can say HFSS is capable of providing different outputs to make sure the design meets the expectation almost perfectly. Last but least is ESD, or electrostatic discharge analysis. Industry surveys indicate that up to 35% of integrated circuit field failures are ESD related. Using full chip level modeling techniques, ANSYS Pathfinder can determine if a design meets EDS guideline or not. It can also identify weak areas of the design, could be on the layout or on the circuit, that are most vulnerable. So this helps the designer to redesign their PCB. As you can see, there is an example of a coffee pot here. So they redesign it and make sure that they follow the EDS guideline. Pathfinder can perform ESD integrity checks on very large SoC design with more than 100 million instances. It handles hundreds of power, ground, and signal nets, and perform resistance and current density simulation in just a single simulation. So it covers all these nets that you have, power, ground, and signal. The analysis is performed at the layout and circuit level to identify and isolate the design issues that can cause chip or IP failure from charge device model, human body model, or any other ESD events. So in the summary, as you can see here, can you hear me? Okay, sorry, I thought my microphone was off for a second. So in the summary, ANSYS can help engineer to decrease number of redesigns. It gives them deep insight to evaluate power integrity, signal integrity, and EMI, so the designer can make sure they comply EMC standard. DCR, as we discussed, improves reliability in terms of thermal characteristic of PCB. ANSYS also helps designer to find weak areas in terms of this EDS guideline, so they can make changes accordingly. And improve antenna design, its location and performance prior to making even the prototype. I hope you enjoyed this presentation. This is the end of this session, and we'll be happy to answer any question. Or Glenn, if you'd like to add something, please go ahead.
Does anybody have any questions at this time? Okay, if I'm not seeing any coming up. If not, just make sure I'm looking at the right. Okay, so Daniel, can you go ahead and go to the next slide? Okay.
Sure.
So thank you for the overview, Daniel. This morning we've introduced simulations available through ANSYS SI-Wave. Over the next 4 weeks, we will take a closer look at additional tools from ANSYS to address thermal and mechanical reliability, as well as predict life expectation. And so a little bit about what Ozone does is in general, these problems, all modeled correctly, any of these solutions can become extremely complex. Ozone Engineering is here to help. In addition to providing and supporting ANSYS solutions, we also offer consulting services with specific experience in FEA, CFD, and high and low frequency electromagnetics. We're here to help you get the answers you need through ANSYS simulation modeling. So if you have any questions about today's session, Daniel, there you go. Please feel free to reach out to us either by email, telephone, or through our website. Thank you for attending, and please remember to register for next week's session on thermal reliability. Thank you very much.